Eli is standing at one end of a football field. He throws the football at a 35-degree angle with a speed of 20 meters per second to his friend Odell, who is waiting downfield to make a spectacular one-handed catch. How high will the football go? How long will the football be in the air? How far will the football go? All right, so this is the second projectile motion problem that we're going to be doing. It's kind of similar to the first. We're still going to have to break our given up into x given and y given. That's the big key with all projectile motion problems. If I were to classify this one, the last problem I did, I classified it as a horizontal launch problem. If I were to classify this one or give it a name, it's a little clunky, but I would say this is delta y equals 0. Okay? Delta y equals 0. However, the object is thrown at an angle. And so the big key to solving this problem will be knowing that this football starts and ends at the same height. Regardless of all the other craziness in the picture, this football starts and ends at the same height. That's important. That means that everything we're about to do works. All right, so like always, we're going to start to put some information from the problem into our picture. So it says that Eli throws this football with a speed of 20 meters per second. And it says that the football is thrown at a 35-degree angle. Okay? So that's the first thing we need to write down. If you look around at the rest of the words on the problem, I don't think it gives you a whole lot else. It tells you we're looking for a lot. It says we want to know how high this football goes. Ultimately, what is its maximum height? So we're going to find that. It tells us we want to know how far the football goes. And I believe it also says we want to know how long the football is in the air. So we're going to have to find all that stuff with just that. First key to doing a problem like this, anytime we have an object launched at an angle, we can't use this. I already said we need to separate our given an x given and y given. This is neither. This has some x and some y. So what we have to do is we have to take this initial velocity vector at this angle, and we need to separate it into its x and y components. So I'm going to get a different color over here so that we can see where I do that. We need to take the initial velocity, and that's what that is, that initial velocity of 20 meters per second, and separate it into Vox and Voy. And so what you can see is I made a triangle out of that. There's our hypotenuse. This is Voy. This looks like our opposite side. And this is Vox, which is our adjacent side. This will allow us to actually get some useful information out of that piece of given. So what I see here is I see Vox is the adjacent side of this triangle, like I just said. So what I'm thinking is cosine of theta will equal the adjacent over the hypotenuse. You got to know your trig to do this stuff. Adjacent over hypotenuse. The adjacent is Vox, and the hypotenuse is VO. And I'm going to rearrange that because you know I like to do that without plugging any numbers. So I get VO cosine theta is equal to Vox. And then we can just plug those numbers into the calculator. So that's 20 cosine 35. Okay? So then you got to go to your calculator. You got to make sure that your calculator is in degrees mode. Otherwise you will not get the correct answer. This is 35 degrees. If your calculator is in degrees mode, you should get 16.38 meters per second. And so there's your Vox. Now I've got to do the same thing for Voy. Voy is the opposite side of the triangle. So I'm going to use sine. I'm going to use opposite and hypotenuse. The sine of theta is equal to VOY over VO. Again, opposite over hypotenuse. Got to know your trig if you're going to do these problems. I'm going to move the VO over just like before. VO sine of theta is equal to VOY. And then just like before, I'm going to plug in my numbers. It all looks real similar. So that's 20 sine of 35. And that equals VOY. If you plug that in your calculator, in degrees mode, you should get 11.47. So now we have some useful information. Now we have VOX, put that in my triangle here, 16.38 meters per second, and VOY, that'd be 11.47 meters per second. Now I usually try and leave all my work up on the board when I'm doing these problems, but I'm clearly going to need more space. So I'm going to get rid of all of the work, the sine and the cosine. So if you need to take a look at that later, scroll back on the video and find it. Okay, now we have useful information. Again, we can't use VO at a 35-degree angle, but we can use VOY and VOX. Now we're going to go write down some X and some Y given. So I'm going to start with the stuff we just found. VOX is equal to 16.38 meters per second. VOY is 11.47 meters per second. So that should help us. Now we're going to start to go to some of the other given that keep showing up in our projectile motion problems. We know the acceleration in the X and the Y. In the X direction, there is no acceleration. There's nothing to make it accelerate horizontally. In the Y direction, we know we have gravity. So this will be AY equals negative 10 meters per second squared. Okay. Last thing that we know, we're going to have to get another piece of given here by manipulating the problem. So what we're going to do is, common theme in a lot of the problems I've been doing on YouTube, we split this guy in half. I'm not even going to worry about the second half. I'm going to erase this over here. I'm going to erase Odell, who by the way has a weird hairdo going on. He's got some kind of neon mohawk, in case you were wondering what that was. I'm going to get rid of all this other stuff here, all this clutter. We're going to focus on delta y max first. And that is going to give us an extra piece of given. Because we know that right at the top of any object's path, it is not going up and it is not going down. Now when we're doing free fall problems, we used to just say VF equals 0. Well, now it's not just VF. Because we have this object moving horizontally and vertically. So right here, what I'm going to say is that VFY equals 0. Because like I said, right at that point it is not going up and it is not going down. VFX is clearly not 0. In fact, it has a constant x velocity. It continues with the same x velocity throughout the entire problem. The y velocity is 0. Okay, so now I have enough y given, I think, to do some stuff. I think, for instance, that I could find delta y, and I ran out of space here a little bit, but I'm just going to write it off to the side here. Delta y is our first unknown. So looking at our equation sheet, I can find one equation that I can use only y given to solve for delta y. I can't use x given. Only y given to solve for delta y. So that looks like this. V Fy squared equals Voy squared plus 2ay times delta y.